Hey guys, these are notes for section 2.5, types of proof. So we're going to talk about some proofs here. A proof is a valid argument in which all the premises are true. So we're going to be basing these on all true statements. We've been talking about converses, inverses, contrapositives, conditional statements. So we've been talking about a lot of statements that could be true or not true. A proof is based on all true statements. Only way you can prove something is by using true statements. You can't prove it if it's false. Before we move on, let me go to the mad gap. There you go. Inner, bod, hull, or, rug, lass. So if you get that one, you can bring it. You can bring it on Wednesday because I'm not going to be here tomorrow. I will be on a field trip. So Wednesday, the 27th, you'll want to bring it and put it in the bucket. Don't put it in the bucket first up. They won't know where it is. And then here's your riddle. If you can figure that out, you can put that answer somewhere. But there's the riddle right there. You need to pause it, but if not, there it is. I'll let you put that over here now. And a little puzzle. I love puzzles, and I love Foxtrot. Foxtrot's cool. Foxtrot. We've got little Jason here. He goes, "Do you like my Sudoku?" And boy, he's got some fun Sudokus on there. So his sister, he says, "You like my Sudoku?" And his sister says, "Aren't you sure you don't mean Sudorku?" Because she thinks he's a dork because he loves math and all this cool stuff. All right, moving on. Proof, a valid argument in which all the premises are true. Okay, the if-then transitive property can be used to make a proof by connecting conditional statements together. Now, we haven't really talked too much about the if-then transitive property. You should know by now what an if-then statement is, a conditional statement. And a transitive property can kind of just hook them all together. It was kind of like our law of syllogism when we did the bird and the fastest bird. If it's the fastest bird, it's the biggest bird. If it's the biggest bird, it's an ostrich. So then the fastest bird would have to be an ostrich. You can go straight from the first one to the last one. That's kind of what transitive property is, where you can go from the first step all the way down to the last step because you've connected other pieces. Here's an example. Prove that if a company takes inventory using a computer, then the company can reduce payroll. So we need a logical chain of events. So our P statement is basically if the company takes inventory using a computer. That's the first part. That's the beginning. Prove that if a company takes inventory using a computer, then they can reduce payroll. Well, we can't go straight from them using a computer to reducing payroll. We got to say why it would reduce the payroll. So you could say that, well, if they use a computer, then the efficiency of warehouse operations increases. Efficiency would increase because the computer would make things go faster. And if the efficiency increases, then you could say that fewer people are going to be needed to run the warehouse. So you can go from them using a computer to them getting more efficient to them needing fewer people. And if you need fewer people, then you're going to save money on payroll because you won't have to pay as many people. So we just made a logical chain of events that helped us prove this statement, that if it takes inventory on a computer, they're going to reduce payroll. So here's the inventory on a computer, and because of that, they can reduce payroll because of these steps. Here's the logical chain with symbols. We started with a P to Q statement. If it takes inventory on a computer, then the efficiency of warehouse operations increases. We went from Q to R, so if the efficiency increases, then fewer people are going to be needed. And then we went from R to S. If fewer people are needed, then you can reduce payroll. So that is just using a logical statement, logical statements to help you prove a statement. And these are all true statements. You can only use true statements in a proof. The conclusion by if-then property is that P would go straight to S. That if they take it in a computer, then the company can reduce payroll. Pause it if you need to. Moving on. We have a two-column proof, one that has two columns. As you can see, there's always a column for statements and there's always a column for reasons. A two-column proof is where one column of true statements, they have to be true, in a logical sequence, just like we showed you before in the payroll example, followed by a second column with the reason for each step. So here's a little example problem. Brittany knows that if mirrors are parallel in a laser, like M is parallel to N, okay, here's your parallel, and then here's the two mirrors. and angle 1 is congruent to angle 3. So this angle here is the same as this one. So you could actually show that by putting an arc here and an arc over here that shows that those are congruent angles. Then the paths of the laser beams along A and B will be parallel. So we want to prove that. So basically what we want to do is try to prove that A and B are parallel lines. Right now all we know is that 1 and 3 are congruent and that M and N are parallel. That's what we know. We don't know that A and B are parallel yet. So we start with a given statement. M is parallel to N. They gave that to us in the problem, so we write given. Now if M is parallel to N, we could say that angle 1 is congruent to angle 2. 1 and 2 are, we just learned about those even more today, that those are alternating and they're interior, and those are always congruent. So alternate interior angles have to be congruent. Letter C is back to the given statement. An angle 1 is congruent to angle 3. They gave us that in the problem, so again we would write given. That's a true statement because it was given to us. Now look at how you've got angle 2 being equal to angle 1, and angle 3 is also congruent to angle 1. That means that 2 and 3 have to be congruent, and that's by transitive property. If they're both congruent to 1, they have to be congruent to itself. That would be transitive. And if 2 is congruent to 3, then A has to be parallel to B, because 2 and 3 are a special name. We talked about those in class today. Those are called corresponding angles. If corresponding angles are congruent, then the lines have to be parallel. That's what the converse says. If the angles are congruent, then the lines are parallel. So angle 2 and angle 3 are going to make these two lines parallel. That's called a two-column proof. You just use logical steps to reach your proof statement. We also have what's called a paragraph proof, and that's a detailed paragraph using a logical chain of, again, true statements. B is the midpoint of AC, so let's draw a segment. Let me draw a point on there, a couple of points actually. Doesn't have to look exactly like this, but it's something close. What we have is we have A and we have C over here. And it tells us in the given statement that B is the midpoint of AC. So this B is right between these two. And that BC is going to equal DE. So that means that D is right here. E is right here. And it's telling us that BC and DE are also the same. So what I'm going to do is, in red, I'm going to put the little tick marks. Because if this is a midpoint, that means that it makes two equal pieces. So since B is in the middle, those have to be equal to each other because it's a midpoint. Now it does also say that BC is the same as DE, so if BC has one tick mark, I need to put one tick mark on DE because those are also the same. They want us to prove that AB is congruent to DE, and we basically just did that because they both have one tick mark. Here's the reasoning. Given that B is the midpoint of AC, okay, so B is the midpoint of AC, therefore AB is congruent to BC by definition of a midpoint. Definition of midpoint says it makes two equal pieces. Since BC is congruent to DE, we can conclude that AB is also congruent to DE because of the transitive property. Again, because congruence of segments is transitive. Transitive property says if AB is going to equal BC and DE is also going to equal BC, if they're both the same as BC, then they have to equal each other. So that's what transitive says. So that was called a paragraph proof, just a paragraph of true statements and going to a proof statement there. Here's the last little page here. It's on vertical angles. It's just a small proof here. In the diagram, angle 1 and angle 2 are vertical. Angle 1 and angle 3, which we understand are a linear pair, they're supplementary. They're making a straight line. 2 and 3 are also making a straight line. We want to prove that 1 and 2 are equal to each other. So they're vertical right now, but it doesn't say they're equal, so we want to prove it. So we would start with the fact that 1 and 3 add up together to equal 180. This one plus this one makes 180. That was right here, and that's the definition of what a supplementary means. It means it adds up to 180. So this is a true statement because of a definition. We could also say that 2 and 3 add up to 180, also the same because of that definition. This definition tells us that these two add up to 180. Now we could say that 1 and 3 are the same as 2 and 3 because they both add up to 180. So we could actually put substitution there. We could take out the 180 and we could substitute in 2 and 3 because 2 and 3 also equal 180. So we're substituting. Then we could say, well, I know now that angle 1 has to equal angle 2 because I could subtract angle 3 on both sides. If you subtract angle 3 on both sides, subtraction property, you minus angle 3 here and minus angle 3 here, they'll cancel out and you'll just have 1 equals 2. So the angle 3's will now cancel out and 1 would equal 2. The measures of 1 and 2 are equal. That means the degrees are equal. You could also say that the angles themselves are congruent. One could land right on top of the other and they would be congruent. And that's the definition of congruence. So we just proved that angle 1 and angle 2 are congruent to each other. Basically, we just proved that vertical angles are congruent. So we made what we call the vertical angle theorem. The vertical angle theorem tells us that all vertical angles are congruent, and we just proved that. All right, guys, have a great day. See you later.